All right. Hello, everyone. Thanks for joining us again for the NeuroNexus webinar that we do every Thursday at 10 a.m. Today, we got a great webinar with Jamie Hetke doing our custom designs. Broadcasting here from Ann Arbor, Michigan. As you can see, I'm in a new office. My boss said I was doing such a good job hosting these that he gave me an office. No, I'm kidding. He's actually in the webinar right now, so I'm just going to give him a hard time. Next week, we're going to do a SmartBox unboxing. That'll be a great one. If you order a SmartBox, we'll look at what you get and describe each piece and set it all up, and it will be really easy, simple to go, and you can start recording immediately. All right, so with that, I'm going to hand it over to Jamie. Go ahead, Jamie.
Okay, so welcome everybody. Today I'm going to talk to you about probe customization. It's a service that we offer here at NeuroNexus. Just a brief history of NeuroNexus. We just celebrated our 15-year anniversary last year, and right before the quarantine, we moved into this beautiful new space. We occupy a little more than half of this building here in the south side of Ann Arbor. You can see that we've been through several phases. We spun out in 2004 from the University of Michigan. We were acquired by Great Batch in 2012, which is now Integer, a medical component supplier. We joined NuVectra in 2016 as a spin out from Great Batch. That's a neuromodulation company. And then we just became independent again last year. We're back to our roots. We're a small business. And we currently have between 30 and 35 people that include engineers, scientists, and technicians. All together, a lot of us have been doing this for many, many years. More than 150 years of collective experience working on thin film neural probes. So you're working with the right people. So you might want to know, why would you want to customize a probe? We all know the brain and the nervous system is a very complex system that doesn't lend itself to a one-size-fits-all technology. We offer many, many catalog probes, so you can take a look through our catalog, but in some cases, the ability to tune an array to the region of interest allows you to maximize the efficiency of your experiment as well as the utility of your data. And so we offer several technology platforms that allow you to do just that. So if you do decide to go for probe customization, this is what you will get. We have application scientists and engineers that have experience in neuroscience. They are neuroscientists and biomedical engineers. So we'll take your design concept, we'll talk about it, we'll evaluate its feasibility, and if it's feasible and we want to move forward, we'll turn it into a CAD design that will be used to provide you with a document that you can look at and approve. So we have a formal design review, and then we fabricate your probe and package and test it. And just a little bit of history here. As mentioned, we've been doing this for a very long time. These are members of the original Michigan probe team, and you can see myself there and Dave Anderson, Ken Wise, Khalil Najafi. Myself and Dave Anderson are still part of NeuroNexus. So we've been doing this for quite a long time. That was in the late 80s. As I mentioned, we offer a vast catalog of probes. There's literally hundreds of designs and packages that you can use to construct most, or electrodes that'll suit many needs. I'm not going to say most. I'd encourage you to look through the catalog if you haven't done so already. You might find something that would fit your experiment, or you might get some ideas for the custom that you're dreaming about. So use that to spark your imagination. And in fact, many of the electrodes that are in the catalog started out as custom designs. So here's my outline. I'm going to just give a little primer on what a thin film probe is, an overview and a brief history of probe design and the techniques that are relevant to design features. I'll describe what our technologies are and the design rules that are associated with those. And I'll take you through a custom design process and end with some examples of successful design projects from some of our customers. So what are thin film probes? You'll often hear our probe technology referred to as MEMS or thin film. MEMS are micro electromechanical systems that are built up using thin film technology used in the integrated circuit area. Here, thin film refers to a conductive or insulative film that is in the range of a few nanometers to 100 microns. The probes that we build, typically the thin films are in the range of submicron to micron. Why would we want to use these techniques to make electrodes? Well, they have wonderful mechanical and electrical properties. Mechanically, you can make them very thin in the range of 10 to 50 microns. Very small features. You can put electrode sites very close together, very precisely placed, very high density of electrodes on a given substrate. So you could put, say, between 32 and 128, well, 32 and 64 sites on a shank that has the same cross-sectional area as a single site wire electrode. So small device footprints. And you can kind of read through the other properties, but one important property I'll mention here is they're batch fabricated. So when you make one, you make a lot. And finally, the design space is very extensive. And we like to say that anything you can draw on a piece of paper, we can make for you. So it lends itself to custom design. These are some examples of areas where NeuroNexus probes have been applied, and it just gives you an idea of the breadth of the design space. We've made probes for use in everything from fruit flies to non-human primates in all of these various areas and more. Here's a cross section through a canonical thin film probe. So if you take a cross section through those that electrode site, this is what you're looking at. And this just gives you an idea of the layers that are used to make an electrode. There's a substrate. Sometimes that substrate is there just for the manufacturing process and it comes off at the end. Sometimes it provides the structural support for the electrode. The dielectrics insulate the thin film leads from the surrounding salty environment. And then the electrode site forms a neural interface to the tissue that you're putting it into. And you see here I've listed various materials for each of these, and we have access to all of these materials, and each has its own merits for particular applications. So we can help you choose what you need for your particular application. This is a thin film fabrication cycle, sort of a generic cycle as shown here, and there are 3 essential steps in thin film processing: deposition, patterning or masking, and etching. And if you start with a deposition panel, you deposit a thin film on a substrate, put photoresist on top of that, and then you enter into the next step of the cycle, which is patterning. And that photoresist is photodefinable, and that allows you to selectively remove it from certain areas of the wafer for the next step, which is etching. And that pattern is transferred down to the thin film below, and you're able to selectively etch away the material where you don't want it. And then you go back to deposition, patterning, etching, and you go around that cycle as many times as it takes for you to make your device. And for this talk, we're really going to be focusing on the patterning step because that's what's really important to design. Okay, just an overview, brief history of probe design and lithography techniques. So when I was preparing this talk, I dug out some old Polaroids of some interesting old designs. You might recognize some of the names on these pictures here. The 2 panels on the left are the original ribbon cables that really drove the chronic use of our silicon probes. The top one is a polyimide cable. You can see it's designed in a coiled shape so that it could be pulled out into a longer structure. It's sitting there by a penny. It was made in the late 80s, to give you an idea of size there. Below that, silicon ribbon cables came along. And what those are, they're actually monolithic with the electrode, but they're thinner. So the cable is 5 microns thick here, and the probe was 15. So the cable was flexible and the probe was stiff, and it gave you a way to plant the probe in the brain and leave it floating, bringing the signals out over the cable. Those technologies are still at the base of our chronic implants today. In the middle there, you see on the top, that's an electrode. It's got some interesting design features that we made for Ed Schmidt and Bill Hedricks at the NIH during the days of the neural prosthesis program. At the tips of the shanks and at the top of the array, you can see holes through the substrate. Those were there for to encourage anchoring in tissue. It has an integrated slotted cable, and these were put into non-human primate visual cortex at the NIH. And I also want to mention they were really the basis for some of the rejuvenation experiments, if you're familiar with that. There's some publications on that out of Daryl Kipke's lab, where if you pass a little bit of current through the sites, you can sometimes rejuvenate activity on the sites after a period of time. Below that is an electrode that came out of Andy Hoffer's lab in the mid-90s. What this was a peripheral nerve implant. You can see it's very sharp. You can also see on the side there are barbs, and those were intended to hold the electrode in place once it was implanted. You'll also see an integrated cable and a little handling tab there that a vacuum pick went over, and then you could insert the array and release the vacuum pick. That was for rat peripheral nerve. Upper right, some of you may recognize the name Greenberg, Rob Greenberg of Second Sight. These were some retinal arrays that we did for him in the early 1990s. Probably some of the first retinal arrays that he designed. They were actually made of very thin silicon, so 5 micron silicon, not polymer. They were very flexible, but they were also relatively rigid, more rigid than the technologies that we make today. But I thought they were interesting, so I included them. And then right below that, that's a sieve nerve implant. So it's intended for use in a transecting nerve. So you cut the nerve, you put the stumps on either side of this array. They grow through the array, and the shiny areas are the electrode sites. And you can record from the regenerated nerve. This was from the lab of Steve Heistein at Washington University in the late 1990s. And what's interesting about this array, in addition to the design is really cool, it went up in the NASA Neuro Lab in 1998. And that was used in vestibular nerve in toadfish. So we've been doing this for quite a long time. One of the things that comes up often when we talk about designs with you is feature size. And so I wanted to mention what feature size actually is. It's the smallest feature, or the critical dimension on a mask layer. Typically, the smallest feature on a probe is the interconnect trace width. So you see a probe here, and you've got the traces here. So the width of these traces, those are the critical features, or the feature size. And it's dictated by lithography and etching techniques. And I'll talk a little bit about that in the coming slides. But you should keep in mind that there's a trade-off between feature size and yield. As you go smaller on feature sizes, yield can become an issue. Again, digging down deep in my Polaroid box, I remembered this early method for making masks. And it was done by cutting a film called Rubylith. And what you see there on the lower left is a guy at the Intel Corp in the 70s cutting Rubylith. And what you did is you drew your design on very thin graph paper and put the graph paper on a light table, put the Rubylith film over that, and you actually cut the Rubylith and selectively removed the areas where you wanted light to shine through. So we actually made the probes on the right using Rubylith in the mid-'80s. And I believe the feature size on these probes was around 5 microns. I don't actually recall. But so once the Rubylith was cut, you typically did it at 100x. For the probes, we did it at 100x. And then that was reduced down onto a glass plate that became the mask. Very labor-intense process, as you can imagine. I can't even imagine making a circuit. The probes were labor-intense enough. And that had to be done for every layer. So now we use techniques with CAD-generated masks. It's still optical lithography. In other words, it's done by shining a light through, through the mask. We talk about mask. I wanted to show mask plate. This plate is 5 inches square. It's actually square. There's a perspective issue because of the photo. It's a chrome-plated glass plate. The data that are used to generate the patterns on the masks are done using computer-aided design. We use 5 masks to make our probes. And I'm just showing them here. The first one is the traces. You can see it's actually at a 5x. And the reason is because of feature size, you want those to be very high resolution. So you use a tool that reduces that down to get the resolution that you want on those traces. This is a contact mask, so it's actually a whole wafer layout. And bond pad mask. Those are the iridium site, or the site mask, and this is the actual outline of the probe. So 5 masks used to make a probe. There's a 4-inch wafer shown with probes on it, and up on top of that you see how the mask is used. It's put in a mask aligner, exposed from the top with UV light. The pattern is transferred to the resist down here, and then your etching is performed, and you end up with your thin film. This technique, depending on the tool that you used or that you use, with a stepper, you can get features as small as 0.7 microns. So I also wanted to show a slide that, in the spirit of continuous improvement of our technologies, we are exploring the use of e-beam lithography to form traces that are much smaller. This middle panel right here shows the technique. A focused beam of electrons direct writes the features onto your photoresist. You can make them very, very tiny, less than 10 nanometers in the industry, which is way, way small for a probe. But the problem, not the problem, but one of the issues with this is it's done in serial. It's a serial process rather than through one flash of light. So it can be very expensive. Cost is high due to the advanced tool and the write time. You would probably only use this for your critical layer, which is the trace layer. And we're exploring this for advanced high density designs, which will have features on the size of 0.2 to 0.5 microns. So you put a lot of sites on a very narrow substrate. Okay, so now on to what our technology platforms are and the associated design rules. We make electrodes that are silicon-based and polymer-based. The silicon-based electrodes are mainly intended for penetrating types of applications, Cortex, deep brain, those kind of things. Polymer arrays are flexible, so they can be used for brain surface, ECOGs and EEGs, or anywhere where, and heart. You can see on the bottom panel there, an electrode grid on the heart. Or they can be used in cases where you need something that can be molded. So you can mold these devices to make nerd cuffs or deep brain stimulation arrays, as shown here on the right. So we'll start with silicon. The silicon process, this talk is not about process, so I'm not gonna go over what our process is here, but I just wanted to show you the layered structure that is used to make an electrode. This particular process takes 5 masks, and I've got some design rules here. I'm going to go into more detail on those in the next slides. One question that people often want to ask is, how wide is my probe going to be? I've got 64 electrodes on there. How wide is it going to be? We've talked about feature size. Well, definitely feature size is important when you're trying to figure out how wide your probe is going to be. You're looking at the trace width, the gap between the traces, this site pad here. Every electrode site has a site pad associated with it where we make contact from the site up on top down to the respective trace. So the lithography technique used to make your probe is really going to dictate how wide your probe is going to be. At NeuroNexus, we have a site formation process that allows us to put sites up on top of the top dielectric, and it actually goes over adjacent traces that are insulated with that top dielectric. So site size does not impact electrode width, which is a great feature of our electrodes. So when you ask how wide your probe is going to be, you know, we're going to have to answer with, well, let's look at what lithography process we're going to use. Some of the customizable specs on a silicon probe are shown here. You can choose a number and length of your shanks. You know, you might have a 4-shank probe with 4 sites on each shank, or an 8-shank probe with 8 sites on each shank. You can choose the length of your shank as well as the thickness, and I'll go over some of those design rules. With respect to the sites, you can tell us how many you need, their spacing, their arrangement, their shape, their size, what material you want. We can guide you on all of those choices. We also offer customized packaging as well. We can customize a PCB if you need stimulation traces to come out separate from recording traces. We've done a lot of that. Site arrangement, this is a page right out of our catalog. It just gives you some ideas of what we can do. Linear sites, tetrodes, polytrodes. Each one has its merits depending on the type of experiment you want to do. So you can also consider combining a couple of these on one probe if you've got a specialized experiment, and I'll show you an example of that. Okay, so here are the design rules, and I'm going to preface this by saying these are their rules, but if there is a compelling reason that you would like to push any of these rules, we are willing to talk to you. Can't always guarantee that we can do exactly what you want, but we're all scientists at heart and technologists, and we love to try new things. So the minimum trace pitch, I have a value here of 1.5 microns. So that means the trace plus the gap between center to center spacing of your traces. If we get to the point where we can make E-beam probes, this will decrease. The site area, 16 microns squared is a very tiny site, but we can do something that small. Let's see, you can read these. The standard shank length I have listed as 15 millimeters. Realistically, you can make a shank as long as, or your limitation is really the size of your wafer, but there's some practical limitations as well. So if you want something longer than 15 millimeters, we might be able to achieve it, but we can also look at achieving that through hybrid assemblies. Our vector electrode is an example of that, where we make 80 millimeter electrodes by combining a silicon probe with a cable and put it inside of a tube. But if you're interested in a longer silicon electrode, just let us know. Shank thickness, 15 and 50 microns. Historically, those have worked great for most applications. We've made probes as thick as 200 microns. We've made thinner probes. So if you've got a reason that you want to go with something different than that, let us know. Just know that there would very likely be a premium charge because you have to sacrifice a whole wafer for your design. You can't do one probe at 200 microns and one probe at 50 microns. They're all going to be the same. And then, of course, we offer a variety of site materials. There's some considerations when you're thinking about your electrode site. Your electrode site is probably the most important feature of your electrode because it's actually the neural interface. So you should put some thought into the design of that. Our sites, if you're wondering why a site is 177 microns squared, it's actually the diameter. We offer standard diameters of 15, 30, and 40. We have a lot of experience with those, as do our customers. In general, smaller is suggested for recording units, larger for recording LFPs or stimulation. I say in general because it obviously depends on the tissue that you're going to be working in. If you're interested in stimulation, we have guidelines on materials and charge capacities of sites, so you can talk to us about that. Placement of the sites on the shank, they can be put anywhere, as I showed you before. Just a kind of a rule of thumb. Again, I'm going to preface it by saying it depends on the brain region, the cell size, those kind of things. But close space sites, 25 to 50 microns, such as shown in that tetrode. They're used when you want to record correlated signals for signal processing reasons. If you're interested in uncorrelated activity, anything 150 microns or more, you're going to see little or no coherency between sites. And 100 microns, you'll probably see some coherent signals and some not. Hopefully you're familiar with our matrix probe line. This is a 3D electrode intended for recording or stimulating volumes of tissue. It's a true 3D probe. On the lower left there, you see 4 probes stacked in what we call a platform. We have a variety of catalog probes that can be put into those platforms, and then we have a number of platform designs that vary in terms of the spacing of the probes. But we can actually customize both the probes and the platforms, and we've done that. On the upper right there, you can also see that with our catalog probes or with the custom design, you can choose to put some probes that have a shank length of, say, 2 millimeters and some that are 10 millimeters, so that you can access the surface cortex with the 2 millimeter probes and the cortex and the deep sulcus with the 10 millimeter probes. So you have a lot of leeway here. Okay, so that was it for silicon. We're going to move on to the polymer process. Typically, these are based on polyimide, although we do have access to other polymers as well. The left panel shows a cross-section through the DBS electrode that's shown on the upper right there. Our polymer process, depending on which process we use, is between 2 and 5 masks. And as I mentioned before, these are flexible arrays for brain surface, spinal cord, heart, those types of applications. What can we customize on a polymer probe? The footprint. This particular example is an ECOG electrode. You can see the small holes there are to allow fluid to pass through so that you can keep an intimate contact between the array and the surface of the brain. It also has a large hole for insertion of a penetrating array. We can customize the shape. By that I mean we can make DBS electrodes that can be molded around a carrier. And like the silicon probes, we can customize how many sites, the site placement, material, all of those things. These usually come with an integrated cable. You can specify the length of that cable, and we can also customize the packaging. Design rules, again, prefacing this by saying if you see something here you want to push, just let us know. But I will say, with respect to the minimum trace pitch, the reason this is larger than the silicon is because when you do lithography on a soft material, the ability to make things very tiny becomes very difficult, if not impossible. So 3 micron traces is kind of our minimum trace width. Generally, people don't need to push that because these are usually quite large devices. The length I have listed is 300 millimeter. We've actually made a device this long. We work on 6-inch wafers. The way we do this is to design them in a zigzag or something like that that can be folded out and made straight. So if you need something very long, it is possible. Maximum overall dimension, if you want to make a big, gigantic ECOG, for example, you're ultimately limited by the size of the wafer. However, remember this is a batch process. So if you're putting one device on a wafer, it's probably not going to be very cost effective using this technology. Okay, so how do you design a custom probe? We're going to go through this procedure. Generally, we start with a custom design request form that you can get from the website or from one of our sales team members. This is it. If the graph paper on the right there, the more details you can provide us with, the better, the more efficient the process will be. Label your design with dimensions, put in as much information as you can on that drawing. And then on the left there, you'll see those tables for the silicon and the polymer technologies, asking in words for some of those critical dimensions. Also, we request a basic experimental description because it helps us make sure that we're in line and offering you the correct choices for the technology and materials and things. So here's an example from Dr. Balint Lasztoczi. He designed an electrode, as you can see here, for use in mouse hippocampus. It's an acute awake prep. And what's cool about this electrode is he actually took two existing designs. The outer two shank are our kind of standard Buzsaki designs, and the inner shank, the middle shank, is a linear array. And the outer two shanks, you can see the lines drawn here, the layers of the hippocampus. The outer two shanks were intended for recording units from the cellular layer, and then the middle shank was for recording deeper LFPs from the hippocampus. And I also point out that you can see the difference in the electrode site size. The unit sites are smaller than the LFP sites. So once we get your CAD design or your design drawing, we take it into some in-house developed design software that we call ProbeCAD. This was developed by our very own Dave Anderson. It's an incredibly powerful software package that allows us to tweak design parameters quite easily. I'm not going to say it's fully automatic, but it definitely takes some of the time-consuming design procedures out of the design, and it allows us to quickly change parameters if you change your mind about something. So the design that I've shown right here is actually a DBS lead, and you can see that ProbeCAD allowed us to make wavy leads. It allowed us to balance the resistance on our leads, which is important in a stimulation electrode. The other thing that this software allows us to do is export the data to our IC design software, as well as some other softwares like the 3D modeling software, SolidWorks. You can take it and we wrap this electrode around a carrier. We could see what it looked like. We also can take it into COMSOL, so we can model stimulation fields, which allows you to look at your design and tweak it if necessary, if you don't like what you see. And I should note that we actually offer modeling as a service if anybody is interested in that. So once you get out of ProbeCAD, you import the data into a Mentor graphics program that is used for IC, integrated circuit design. And that's what you see here. This is the output of IC Station. This particular program is used to generate the data that we send to the mask maker to make our glass plates. And it's also used to output the design for the design review. We will have a design review with you, send you this document. You make sure everything looks okay. If it doesn't, mark it up, send it back, and we'll just iterate on the design process until we get it right. Once the probe has been approved, it's added to a die on a wafer. So what you see here is an exploded view of a probe. The pink lower layer is the outline. The next layer up are the traces. After that are the contacts, and then the gold bond pads are on the left and the sights are on the right. So again, 5 masks. It's added to a die, like you see here. That particular probe, I think, was replicated 2 times on this die. It just depends on how many probes are going on a die and how they all fit together. It's like putting together a puzzle. It's actually one of the most fun parts of the design process. And then once you have your die, or you can have multiple die on a wafer, they're laid out, you get a whole wafer layout. And then if you're gonna use physical mask plates, they're ordered from the mask vendor at that point. Here's the design successfully fabricated, that I showed you, the Hippocampus electrode. Okay, now I'll move on to some custom design examples. Everybody is very likely familiar with Dr. Yuri Buzsaki. He's our most prolific custom designer. He began custom designing silicon probes with us during the Michigan days in the early 90s. The Buzsaki probe that you're probably very familiar with, the kind of polytrode at the tip, came out of those collaborations. He's probably designed on the order of 20 to 25 different designs with his lab with us. Many of them are in the catalog. Some of them aren't in the catalog yet. They're going to be really cool though. This is just a spectacular example of the power of silicon probes. He's able to map a plane of Hippocampus with one fell swoop with a 256 channel electrode array that we did for him. And his website, if you have not looked at his website, it's absolutely beautiful, and all of his publications are on there, and many of them are available as PDFs. I encourage you to take a look at those. This example came out of the Max Planck Institute. It was designed for lizard cortex. This is what we call a polytrode, very closely spaced sites. Again, lizard cortex, and you can see 64 channels of data coming out of, actually it's 32 channels of data coming out of lizard cortex there. Worked very well for them. Out of the lab of Dr. Paré from Rutgers University, this was an electrode designed for rat amygdala. It's a chronic preparation. And this also illustrates the importance and beauty of custom design. In the lower right there, you see that he wanted to fully instrument one plane of the amygdala, the rat amygdala, with an electrode. So he adjusted the shank length, the 2 shanks on the left are longer than the 2 shanks on the right, and adjusted the spacing of the tetrodes so that he got the optimal placement. I think you can see the spacing on those tetrodes is 333 microns. So he was very precise in terms of where he put those tetrodes. And there's a publication listed there that resulted. This is a more recent design from Scott Pluta of Purdue. It's very neat. What he wanted to do was just record from as many neurons as he could in the awake behaving mouse brain. And so they're very densely packed electrodes spaced at 20 microns. And he tweeted out, he's very excited about this electrode. This was just a couple of weeks ago. And we're really excited to see his results from this. Lizette Menendez de la Prida is a customer of ours who has also designed many, many different electrodes, including EEGs, penetrating electrodes, and these slice electrodes, which are now part of our catalog. And these electrodes are kind of unique because they only have 1 site per shank. So it's our only 1 site per shank electrode. So it's a 16 by 1 instead of a 1 by 16. And she's had good results with these electrodes in vitro in rat brain slices. Here's an example. So those were all silicon. Now I'm moving to polymer. Here's an example of an EEG electrode that we did for the University of Edinburgh. This particular electrode, the design actually resulted from a design that Dr. De La Prida submitted to us. But what they did is they reduced the number of sites and added 2 EMG wires. So these are EMG wires. So there are 14 sites on the array and then 2 EMG wires. And you can see the EMG data and the EEG data on this panel down here. And it's kind of fun to design EEG electrodes because the specs are given in terms of the coordinates with respect to bregma. It's a kind of a neat way to design an electrode rather than just specifying a site distance or a site spacing. Dr. Matt Johnson and Jerry Vitek, they have worked with us on the design of DBS electrodes for non-human primates. And this was a full-scale design project. So we designed the electrodes with them, as well as the packaging, the implant, and even went so far as to some of us participated in the experiments with them up at the University of Minnesota. And if I haven't said so already, if you are in need of the service of having somebody come out and work with you on your implants, we also offer that. We have some very experienced people that can do that for you. This particular electrode, they designed two, one for globus pallidus, one for STN. The electrodes had 32 stimulation sites and 8 recording sites. And you can see here some recordings from, I can't remember if this is GP or STN, actually it's both, as well as some modeled stimulation fields. You can use these electrodes for current steering because you have electrodes all the way around the circumference. Doctors McEwen and Moran have worked with us to design sieve electrodes. These are actually polymer based, unlike the silicon one that I showed you toward the beginning of the talk. The array has spokes that have electrode sites on these spokes, as well as on this circular area here. You can see that. So the spokes have sites. They transect the nerve and then grow the axons through the nerve. And you can see here successful growth and recordings of regenerated nerve tissue. And this is a very old design, but it's probably the coolest design I've ever done, and I wanted to show it. It's a chick in the egg probe that we did for Dr. Steve Goldstein in the mid-90s. And what this is, it's an electrode for use in embryonic chick leg. And the experiment, which I actually got to see, they took an egg, cut the top off, pulled the little chicken leg out, stuck the electrode in, and it was a stimulation electrode. And when they had the electrode in place, they put the egg top back on and put it back in the incubator, and they did their experiment. Very neat. But what's neat about this electrode, it has a number of features. You can see the long shank here. This is a Polaroid, so the quality is terrible, but there are holes through the shank that were there to accept a stabilizer pin. The pin's not in here, but it would have gone through here to hold the electrode in place. This is a handling tab to be used during surgery, surgical placement. It's got a slotted silicon ribbon cable. Just a really neat probe. So obviously we customize electrodes, but we also customize cables. I mentioned the 3D assemblies, the matrix assemblies, micro drives, chambers, the packages, adapters, pretty much anything that you need to go with your electrode. We're willing to work with you to customize it if we don't have it in our catalog. Just ask. Please don't hesitate to contact us. So hopefully I set the stage as to why you might want to customize a probe and how you should go about it.
All right, Jamie, thank you so much. So we're going to go ahead and end now. Thank you very much for attending. And don't forget, next week, May 21st at 10 a.m., we're going to do a SmartBox Pro unboxing. So don't miss that one. Thanks a lot, everyone.
Thank you. Bye.